Okay. So welcome to my third live stream, kind of second, because the second one actually got deleted because I didn't have my microphone on, so that's unfortunate. So here we go. We're going to do some math today. So if you have questions, feel free to throw them into chat, or you can also try tweeting me at KStevMath, and I will do my very, very best to respond to your tweet. I'm trying to make sure that this is actually live because it's not showing up on my thing. Oh, yeah, it looks like I'm live. Do I have sound? All right. So the topic I picked out today is what I'm about to do in my Algebra 1 class. So it's super convenient then that I can share that video with anybody who misses. But if you do end up having a question that you'd like for us to discuss, then you just need to let me know in the chat or by tweeting at KStevMath. So I'll just write that out. I will not write it out. Oh, okay. I'll just write, oh, there it is. How do I make an @ symbol? Not like that. How did I just forget? Okay, at KStevMath. Okay, that's how you're gonna get to my Twitter. You can follow me, you can ask questions, that sort of thing. Hello, Math Gives You Power from Dallas, Texas. I am from Texas originally myself, although that's not where I'm at right now. So, welcome. All right, so if we think back to what we should already know at this point, if we're trying to, what are we trying to do? We're trying to find rational solutions of polynomial equations. What we've done previously to this is we've talked about factoring polynomials, which is one way to allow us to be able to find the zeros. So just kind of an example to review that concept is here we've got this polynomial, and when it says find zeros, what it wants us to do is basically say set this equal to 0 and solve your equation. It also has a connection to the graph, that if I graph f of x equals 2x cubed plus 10x squared plus 12, then the zeros are where my graph crosses the x-axis. So we go through in math like all these different ways to solve quadratic equations, and they're great, and one of them is factoring. And then whenever we get to polynomial equations, we find like that are higher degree, we end up finding that, well, they're really the easiest way for, I feel like that did not switch my slide. Hang on. It's a work in progress for sure. PowerPoint slideshow. Anything? Nope, that's still the same thing as it was. How do I get it to change? This is awkward. PowerPoint. This is gonna help. Nope. Nope, didn't help. Sorry for this trouble, all of the above. Right. well, hey. Okay, well, it's not really how I wanted to do this, but it got the job done. Doing some more troubleshooting. This is definitely a work in progress. A work in progress. Okay, I'm gonna stop and restart. Let's see if this makes... Hello, hello. Hopefully this works better this time. We'll see what happens. Alright, so I'm just going to give this a try, because I don't think I'm going to... Oh, now it's green. Well, that's helpful. Okay, so I'm going to walk through this lesson on finding rational solutions of polynomial equations. And so this is kind of in the middle of some things in Algebra 2, or you might see the same thing in a pre-calculus class. And so that means that it may be that, you know, you may be a little lost if you're not in one of those classes doing kind of a similar thing. So some of the background info is that recently in our class we've factored polynomials. We've reviewed that from Algebra 1 and then built on our skills. Something else we've done is long division and synthetic division of polynomials, which is going to be helpful here. We relatively recently went through the different ways to factor quadratic, not just factor, but solve quadratic equations, which is factoring as well as using the quadratic formula and things like that. So basically the problem becomes that when we have a higher power for polynomials, we don't have this nice formula that always works. So we're stuck either factoring or doing something else, which will be later on in the video. So some of the time we can factor. So to refresh our minds there, I've got example 1 here. Find the zeros of this polynomial function. What that's asking us to do is to find where this graph intersects the x-axis, or another way of thinking of it is to find where this equation equals 0. That would be another way of putting it. So what we want to do, it tells us to do it by factoring. We want to always there's supposed to be an x right here. Need to fix that. That's good. We always want to look at the whole polynomial and say, does it have a common factor? And so we look at this and say, everything can be divided by 2, everything can be divided by x, and then we divide everything by that 2x to see what would be left over. So we do x squared plus 5x plus 6. And then if we can, we want to go a step further, because x squared implies that we have 2 more answers kind of going on here. So it's our hope that we can factor to do this, and if that's not the case that we can factor, we could use the quadratic formula to finish solving. But it says to do it by factoring, so we must be able to factor. When I factor this, I want to say what multiplies to get 6 that adds to get 5. And so that's 3 and 2. And so when we find the zeros, and we've got it factored out like this, we just have to set each part of this equal to 0. This is called something about a zero product property, that if you have multiple things multiplied together that are supposed to equal 0, then you need to think about what makes each of them equal 0. So the 2x gives us an answer of 0. The x plus 3 gives us an answer of -3. And the x plus 2 gives us an answer of -2. And it's likely that you don't actually have to sit there and solve all those. Our answers are 0, -3, -2. That's all well and good. But what do we do when we can't factor? That either we don't know how, or just something in general has maybe, prevented us from being able to factor this like we want it. So what we want to do is look at some other possibilities. So this is going to let us use the rational zero theorem, which I have to say is a great theorem because it solves an issue for us of not being able to do anything with higher degree polynomials that do end up having some rational zeros. So remember that the term rational refers to anything that can be written as a fraction. And so that means that 2 is a rational number because you can write it as 2/1, or 1/3 is a rational number because it's written as a fraction. And so yes, integers, yes, whole numbers, but also nice fractions like this. What wouldn't be a rational zero would be square roots or imaginary zeros or complex zeros that have an imaginary part. Those wouldn't be a rational zero. So this theorem looks a little intimidating. This is saying if this polynomial that's in standard form has integer coefficients, then every rational zero of it has the following form: p over q, where p is a factor of the constant term a0, which is this right here, and q is a factor of the leading coefficient an, so this right here. So in other words, if a polynomial has a nice zero that's a whole number or a fraction, and it's also real, it has to be some combination of a factor of the last number over a factor of the first coefficient, assuming that the polynomial is in standard form. So how is this helpful? We're going to use synthetic division to help us guess a zero when we can't factor, and then hope that we can factor the result. So before we do that, let's look at 2 more theorems that help us with this. So one of them is called the remainder theorem. So if a polynomial f is divided by x minus k, then the remainder is r equals f of k. What that means is if you want to know like f of 5 on a polynomial, you can actually use synthetic division with the number 5, and the answer is the remainder that you get from synthetic division. So in other words, here I've got this example: use synthetic division to find f of 4. So the way we used to do that is we would plug in 4 for all of our x's and do some math, and this would be frustrating to do without a calculator. Not too bad with a calculator, but still kind of annoying to have to type it all out, because we have to do 2 times 4 to the 4th minus 4 times 4 to the 3rd, and so on. This theorem is telling us that if we divide by the factor x minus 4, which for synthetic division means that we need to use a positive 4, if we divide and we just take the coefficients for our synthetic division and put them here, then what ends up happening is the remainder here is what we get for f of 4. So here's synthetic division. You drop the first number. 4 times 2 is 8. Negative 4 plus 8 is 4. 4 times 4 is 16. Negative 11 plus 16 is 5. 4 times 5 is 20. Negative 24 plus 20 is negative 4. And 4 times negative 4 is negative 16. So these add and get 0. So f of 4 is 0. Well, what that means, if we look at the bottom here, the factor theorem, that means that x minus 4, because this is going to be the opposite in our factor, that means x minus 4 is a factor of 2x to the 4th minus 4x cubed, blah, 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 which I wouldn't have been able to know that without going through this process. And so, because it's a factor, what I could do is I could rewrite this out now with x's. So remember, it starts 1 degree less than what we started with. So what we basically have just figured out is that we can do this step right here. We can say I can take out x minus 4 from all of these using division. And so then here's what I have now as my new polynomial. Now for this particular polynomial, that's not super helpful necessarily because I don't know how to factor this now. So ideally, we'd know how to factor that, or if we don't know how to factor that, then we would, we'd have to try it again, basically. We'd have to pick another number to use synthetic division with. And so this is going to end up leading us into something that we may or may not be super happy about. So, I just realized that I want to sorry for that interruption. And oh, my head is in the way of the theorem. Get out of the way, head. It says a polynomial behind my head. That's funny. Okay. Here we go. So let's put this all together. What we've got now is we've got a problem here. And that problem is that it did not save the changes. I didn't save the changes to my PowerPoint. So the problem is that I don't have all the examples I wanted to have. That's sad. That's okay. What we have here, and the way that we would try to use this then is, no, I didn't say, this isn't Algebra 1, this is Algebra 2. And pre-calculus. I've done it in both classes, so this is definitely not an Algebra 1 topic. So this idea would be, they're actually giving us a 0, -5, and so we take that -5 and we do synthetic division, and then we're going to look at what we have left and see if we can factor it. So I'm going to put the 3, the 21, and the 26, and the -28, and the -40. I'm going to do some synthetic division, so I'm going to drop the 3. I'm going to multiply -5 times 3, which is -15. 21 minus 15 is 6. -5 times 6 is -30. 26 times minus 30 is -4. -5 times -4 is 20. -28 plus 20 is -8. And -5 times -8 is 40. Now if they give us a 0 like this, we better get 0 here, otherwise we've done something wrong, because they told us, hey, this is a 0. So what this means is that I know that x plus 5 is a factor, and now I can look at the polynomial 3x cubed plus 6x squared minus 4x minus 8, and I can say, okay, can I solve this now? Can I factor it? I was a little worried at first, but I think that this factors by grouping, which is nice, Because if it doesn't factor, then what we would have to do is use the rational zero theorem to try to guess some factors, and that would be, I don't think that's going to happen in today's video. Like I said, my notes were not what I thought they were going to be. So when we factor by grouping, we look at the first two and we say, what do these have in common? They both have a 3x squared. So we take out that 3x squared and it leaves us with x plus 2. Then we look at the last two and we say, what did they have in common? They have negative 4. And then we take out that negative 4 and we get x plus 2. So then we notice, hey, our parentheses are the same. So we write down our parentheses and then we write down what's left over right here when we take out the x plus 2. And then we remember, okay, we also need the x plus 5 from before. And we think about this factor right here that has an x squared and we say, can I factor this further? And unfortunately we can't. If this was a 9, then we could split it up because that's a difference of 2 squares. Since it's not something that you can square root, we can't factor it further because what we're getting isn't going to be rational. It's going to end up being a square root. So finding the rational zeros means we know the negative 5 from before, and then this is going to give us a rational 0 of negative 2. So our rational zeros are x equals negative 5 and x equals negative 2. Hello Sarah, welcome to the stream. Thanks for joining me. I was working on some algebra 2 here, but what are we doing in math class in algebra 1? Because that seems like more fun. We've been doing solving systems of equations. So Sarah, can you solve this system of equations for me? Let's see. Sarah and Sophia, super cool. Thanks for watching. Hey, can you solve the question that I'm really hoping is on the screen? Let me check it out. Let me make sure it's on the screen. It should really be on the screen. Okay, solve this problem. Show off your mad skills. I'll give you a head start and then I'll go for it. I guess I need to make sure that I account for some lag between whenever I say stuff and when you see stuff and then would type back. So we have in the math class I'm teaching algebra 1. We've been working on the 3 methods that we typically learn for solving systems of equations, and so this is set up really nicely to do what's called the addition method or the elimination method. And so I think you're right, Sophia. And definitely math gives you power. You're on the right track as well. We would add our 2 equations together and say that 2x equals 14, and then we would divide both sides by 2 and get x equals 7, and then we'd have to plug that back in to find the other one, which is pretty easy here. You might not even need to write it down, but 7 plus y equals 4. So Sophia and Sarah, great job, because y equals negative 3. Now, Sarah, you did not put it in parentheses, so how's the world going to know that you're referring to a point if it's not in parentheses? So don't forget about that. That was great. How about we do a harder one? And this is the point where you're going to say, I'm never going to watch your live stream ever again, because now you're making me do math. That's okay. I might survive. Let's see. I want to make this work nicely-ish. So, let's see. Alright. Let's see. Sarah and Sophia, can you figure this out? Don't give away the answer. Math gives you power. You're a math teacher, so, you know, that's cheating. And it may not be elimination that you use, because we haven't actually talked about problems like this with elimination. We split it up into 2 parts. So this is something that we'll learn how to do tomorrow. Yes, math gives you power. That is correct. That's one way of doing it, but it's not the only way. So we could go back and remember all the way back from before Thanksgiving, and we could subtract the 5y over so that we can do substitution and say x equals negative 5y plus 10, and then take that and plug it into the other x. Sound familiar? Yeah, so hard when there's Thanksgiving break in the way of these sorts of things. So yeah, we could just say, oh, I can solve one of these for x, and then distribute, or plug it in and distribute all that jazz. So negative 10y plus 20 plus 12y equals 14. So negative 10y plus 12y is 2y. And then we want to subtract 20 over and divide by 2. And I'm really excited because at least this far, this is a nice number, and I definitely made this problem up on the spot, which may or may not have been my best move. So y equals negative 3, and so we plug that back in to find x. Yes, y equals negative 3. Can you find x? Well, this definitely worked out to be a big number. Relatively big. Not really that big in the broad scheme of things, but most of ours end up being like between negative 10, the problems that we work in class. So either I messed up, which I don't think I did. Don't think I did. So 25 comma negative 3. So this has been fun. I'm working out kinks on this whole live streaming thing, so thanks for putting up with me, and until next time, have a great evening. Keep doing math. Keep having fun. And